My name is Anatoly, and I'm one of the co-founders of Solana, and I'm the CEO. And Solana is a high-performance blockchain, and the main difference between us and Elrond and a lot of other folks is that there is no sharding. Sharding is really hard. So the things that they're working on, those are really incredibly difficult computer science problems. And we took a different approach. It's maybe easier for us because of our experience working in embedded systems and hardware. So our approach to sharding is really to build a software stack that can get out of the way of the hardware and really utilize everything that's available in modern day semiconductors, and specifically GPUs. So if you guys are familiar with NVIDIA, a modern day 2080 Ti card can handle about 1 million and to 5519 signatures per second. So that many cryptographic signatures per second in a single GPU card. We just have to write software that can get out of the way and actually get transactions in there and send them around. But beyond just GPU programming, we have a secret open source secret sauce called proof of history. So what do I point this thing to?
Just a second. It's good kind of work right now. Yeah. Great.
Yeah. There we go. So what's proof of history? Just to give you guys some background, around 2017, we had this huge explosion in ICOs. Everyone was crazy about blockchain, and Bitcoin transaction fees were $60 per transaction, kind of insane. And one day I had too much coffee and I was up till 4 in the morning, and I realized that using the same technique as Bitcoin, the SHA-256 pre-image resistant hash function, you can create a data structure that represents the passage of time. So the way it works is the technique is called a verifiable delay function. It really consists of 3 features. It's a puzzle and a challenge that takes a fixed amount of time to solve, that it cannot be parallelized. No matter how much electricity, how much money you actually have to spend real time to solve it. But the time to verify is much faster than the time to solve. So this thing is called the verifiable delay function, and our approach is a very, very rudimentary implementation. It's incredibly unsophisticated, but it works really well on modern day hardware. So Intel has SHA-256 instructions baked into their chips, and these are running almost near the top speed that you can possibly build with a custom semiconductor. So we have a very good understanding of how much faster an attack using a custom ASIC can be. And within the bounds of that speed up, we can build something that uses this process to create a clock in a distributed system. And how it works is to simply take SHA-256 and you spin it in a loop. So its output is the next input. So this thing that runs in a loop over and over itself, because SHA-256 is this cryptographic pre-image resistant hash function, you cannot predict what any of the values are going to be, and therefore, if you sample this data structure, if you sample this process, you create a data structure that can only have been generated by using real time. And somebody somewhere on a single core, on a single thread, on some single CPU actually took the time to run this. And you can calculate how much time roughly it took. So, imagine I had the New York Times with me and I took a picture of myself with the New York Times, and that guarantees that I was alive after that New York Times photo was taken. I think Bitcoin, the original block, right, is the hash of some, I forget what title of the New York Times page. But what's interesting is that if I take that picture and then I publish it next day in the New York Times, that guarantees that it existed before before that second use pair was published. So now I have an upper and lower bound. So same thing with SHA-256. If we have this process that's spinning, if you take any of these samples that are generated and you reference it in a message, that guarantees that the message was created before, was generated right after this sample was created. If you take this message and you insert it into this process, it guarantees that the message was created before the insertion, because you're modifying this pre-image resistant hash function in this unpredictable way. So now you have an upper and lower bound of time when an event occurred. So imagine we now have a way to record cryptographically when anything that's ever been created, right? Like any digital event was ever done. And this guarantee is infallible, right? That you can actually verify it. So when you take a picture with a camera, and that says that this picture was taken on July 22nd, at 12 p.m., somebody could fake that, right? They can modify that. With this approach, because this is embedded in this cryptographic process, it can never be modified. So you have this guarantee that this is the true point in time. But it's not an absolute measurement of time. It's a relative measurement of time relative to all the events that occur in the structure. So what's cool about this is that we can build something very, very boring called time division multiple access. So if you guys ever, if you're familiar with radio networks, early wireless networks, people would set up towers and they would transmit over the same frequency, and when they did this at the same time, they get noise, right? Because they're both occupying the same frequency at the same time, and those things interfere. So what they realize is if you give everybody a clock and you synchronize the clocks, you can split up the channel by time, so every second you rotate who gets to transmit, and they call it time division multiple access. So early cell phone protocols use this. Modern day, 5G, still uses time division to some aspects, along with frequency hopping and a bunch of other optimizations. But at the end of the day, you have a bunch of folks that want to transmit something, some information, or produce a block, and they're trying to figure out who should produce a block first. Bitcoin uses this random process, but the difficulty, what we can do is we can use this sequential hash function to define what time is, and therefore have these block producers schedule at a very exact moment in time, as it's described in the data. Why is this cool? Is because unlike Bitcoin, we never have a collision. We know exactly who the block producer is supposed to be and when this should produce. But what's really interesting about this is that none of the participants in the network actually rely on time. If you are familiar with Tendermint and modern day distributed systems, when messages are sent across the network, they carry a local timestamp, or they potentially trigger a state transition. And nodes, because they never trust each other, they're adversarial, they have to filter out messages that are too old or too new, or they use a local timeout before they transition state. So kind of what I like to talk about is in Tendermint, imagine you are in the pre-commit state and the next block producer sends you a propose because they're adversarial or their clock is running early. You would queue up that propose, you would wait until this current block is finished. So imagine that instead, the next block producer sends you a proof that time passed. You could take that state transition immediately because that proof is correct. You anticipate that everyone in the network will interpret it as correct, and it will also take the same action. Now you can move forward without actually waiting. So because of this property, we can schedule all these leaders using data. What they're transmitting to us is proof that time has passed, and the state transitions can occur instantly. And for our testnet that's live right now, this period in data is 800 milliseconds. and our goal is to ship with 400 millisecond blocks. To me, this is like the coolest thing in blockchain, because now what we're talking about is like dApps that are running with the same kind of user like state transitions that are as good as AWS. Like if you use AWS, you're using S3 and a bunch of other APIs, you're likely to see about like 150 millisecond latencies. Like going to S3, getting like these REST responses, talking to a bunch of their databases through HTTP. You can obviously do a lot faster, but like, you know, if you're lazy, then you just kind of build something. That's what you'll see, and that's good enough. 400 milliseconds is not there yet, but it's pretty close. Like we can start getting dApps that have the user feel that humans actually can deal with and be okay with. Like when you click a button that does a state transition on chain and gets some finality, if that's half a second, humans are going to be okay with it, you know. I'd like it to be 200 milliseconds, but that's going to take a lot of blood, sweat, and tears. But this is like one of the most exciting things about this approach. So what else is interesting? This is like a long presentation, so I'm going to kind of skip ahead. So how we actually deal with BFT, you know, the classical approach is if you're not a proof of work system, you're a proof of stake system. And I think anyone that's building a proof of stake system needs to realize that they're building a BFT, right? Some version of BFT. Because we're still bound by cap theorem, consistency versus availability, you know, safety versus liveness, there's no way to cheat that. We have to be a little clever about speeding up these block times. Because what does it mean for you to have a 800 millisecond, 400 millisecond block? It means the network has to come to a decision that this block has some finality. And if you cut that time to be too low, you're basically cheating safety. That there's no way for a globally distributed system to actually come to a finality decision that's really guaranteed within that time. So what we do is we let the system decide a very, very small amount of safety, like a very small amount of commitment in that 400 milliseconds. So when Alice proposes a block and anyone votes on it, what they're voting on is a commitment to safety for just 2 slots for 2 blocks. And that is roughly, you know, let's say 1.6 seconds. That when Alice votes, and Alice does this decision as fast as possible, because these blocks are coming really, really fast, Alice takes a very small amount of risk. But when Alice votes again, and takes this commitment again, her previous commitment doubles, right? So this now becomes this exponentially growing function. And this is how we're able to build a BFT system that has this pipeline approach that can generate blocks at a high frequency, but allows for validators in the network to take this risk with a very small amount of commitment to safety. But by the time this thing actually gets to, you know, let's say 4 blocks, this block has already been finalized to a commitment of 16 slots. And what that means to this validator is in this historical record of these 4 blocks, they've observed other validators voting on this, right? They've observed other validators voting on this fork, and they can make the decision that, hey, I see the supermajority of the network, they're all continuously voting, everyone is still alive, so I can continue voting, and I can continue to increase this exponential lockout. So that's a very clever bit of how we're able to create this like kind of streaming high frequency block production while still maintaining, you know, BFT. There's a bunch more stuff, but I don't want to like I don't want to take an hour. So like questions. What do you guys want to know? We have a testnet that's up and running, and we're currently kicking off our version of Game of Stakes. It's called Tour de Seoul because, let's see, 4 of the 5 co-founders are Ironman triathletes. I was before I had kids. So Yeah, if you guys run a validator, please join the Testnet. It's going to be a lot of fun. We're going to do a bunch of performance events and see how our software stands up to some like high throughput transactions. The next stage is going to be executing a decentralized exchange contracts. So given that we're like a high performance network that is not sharded, what is the obvious thing that we can build? It's a DEX, right? Because it's a single marketplace, there's no arbitrage, and you can trade things at a near high frequency, so it becomes like a very cool application. You know? So things like that. Cool. Questions? Yes?
Yeah, so do you achieve absolute safety given a particular assumption of like max faulty nodes relative to total nodes? Or do you achieve probabilistic safety but asymptotically negligible?
So after the 32 votes, right, you have 2 to the 32 number of slots. At 400 milliseconds, it's 53 years. And we basically say that just because a smart contract that keeps track of these votes, we don't want it to be infinite, so we fixed it to 32 votes. When you hit that 2 to the 32 number, that's the maximum commitment you can have, and that's when you generate a reward. So in that sense, the protocol gives you full finality at that point, but it's from an application's perspective, depending what you care about. Like if it's a game, you may only want 400 milliseconds of confirmation. If it's a payment, you may want like $10, and you want like a few blocks. If it's $2 million transfer, wait for the whole 16 seconds, right?
Yeah. But what happens in the case of a network partition where different forks vote on conflicting transactions?
Yeah, so...
Sorry if I'm...
Perfect, dude. This is the next slide. So imagine you had a partition, Alice, Bob, and Charlie, Dan, and Eve. So Alice and Bob are in one partition. They're voting, and Charlie becomes the block producer. And because Charlie did not observe this other branch, Charlie produces a fork that has this empty version of the ledger, right? So Charlie simply runs their SHA-256 loop and generates a proof that they got to their slot, right? They produce a block. So both Alice and Bob are locked out, right? But eventually their lockout expires and they get rid of that state, right? And then they vote. That's basically how it works. So the longer the partition that Alice and Bob are in, the longer the lockout is. But Alice and Bob are greedy, right? So when Alice and Bob are voting, they really don't want to vote on a ledger that doesn't have the rest of the network voting with them. So when they make that decision to vote, they're looking at their historical record. Does the rest of the network has commitment as well? And that is actually our weight choice rule. When you look at two forks, you look at the state-weighted lockout of both forks, and you pick the heaviest one.
But in principle, although unlikely and maybe not resulting from rational validators, you could have two forks which are in approximately equal height fragment, right? If there was like a near 50-50 number range.
Right, but since validators are greedy, they will stop voting because they don't want to commit themselves to being locked out from the fork that doesn't have supermajority. So they still look for this, supermajority magic number. You guys use what? It's the 2/3 plus 1, I imagine.
Yeah.
As your supermajority. So.
Squares.
Yeah.
Yeah.
Same thing. So every validator waits until they see a supermajority, right? Plus 1.
Good question of that, totally.
Yeah.
How does it work with regards to what are the incentives to not double vote on either fork? Is there slashing for double voting? So if I'm like Charlie, right?
Yep.
Supposedly I vote on both petitions, not because I'm badly connected, but rather because I've disconnected everyone badly and I'm very low.
Yeah, so slashing sucks, but that's the only thing we can think of. We're not clever enough to get rid of slashing, like Algorand and I think Avalanche doesn't have slashing, so I honestly don't trust those systems, but I don't understand that you can have a mistake without slashing. There's something that like doesn't grok because you simply can't observe every possible partition. Yeah.
Yeah, I'll just keep asking questions. So does this consensus algorithm, can you summarize the votes into like a transcript of signed commits where you are like-minded and you have validated
Yep.
at some point in time, but you don't have the ability to verify this like hash chain? Can you still like verify the commits and assuming a supermajority or rational or something?
Yeah, so you can, what you can do is like effectively like a linked list where the next vote has the previous hash as well. So that's what we do. It's fine, like it's weaker I think than verifying the full hash chain. But
But you still get safety, right? You just don't get composer correctness?
yeah, you don't know if like it's kind of like the same problem with like lines. You don't know if the state transitions are valid. You just know that everyone voted, but it could have been because of an exploit, right?
But you would have the same like equivocation false where the like client would be fooled under the same conditions if
Yep.
it would be fooled.
Yep. So this was our private permissioned deployment on a single Google Cloud 800 megabit network. What's cool is it's actually saturating the switch. And the reason why we're able to get to 185,000 TPS is because we're not rotating the leader. So a single leader running forever until failure, we can actually replicate that many state transitions with a mean confirmation of 1 second. And this is like a theoretical maximum. So it's a really cool achievement. Of course, in an open permissionless network that was globally distributed, this number is about a third. So we see somewhere between 40 to 60,000 TPS, and it's going to take a lot of work to get there because like the next set of optimizations that we need to do is effectively like ahead of time execution of transactions and like caching that state and hoping that the next block has it as a host. So things like that, like are the next level of tricks. Cool. So yeah, TPS. Does anybody care about TPS anymore?
Business.
Yeah.
And this is what state, what's a transaction? Is it like empty or?
So at 5519 signed move from one of balance from one account to the other.
Do you think that if you were to do in a transaction 10 major operations for a DEX or something, this would slow down substantially, or is the bottleneck already at the network layer and it would take a while for it to translate?
So like we use a register-based VM that's Berkeley packet filter, so it can JIT directly to x86. So for like a DEX or something like that, where all you're still doing is compare two prices, and then just most of the work is getting to that point in the pipeline because you're fetching memory from disk, right? You're like setting all this up. I don't expect like 10 instructions, 10 more x86 instructions there to have any impact. We have our transaction format allows for multiple instructions to be sequenced in the same transaction. And that we see about 4 or 5x more instruction throughput. But those are all like atomic, right? So if any one of the instruction fails, we don't commit anything. So this is like more of a fairish comparison, but still this is a permission deployment on Google Cloud, 800 megabit network. That's all running on the same switch.
Are you F-syncing to disk when you come in? Like
Yeah. But we use a memory map file, so that to the operating system. But in these tests, it's more than 10 million accounts, so it's definitely hitting the. It's not enough to. There's not enough RAM to do this all around.
Have you done any kind of real-world setting tests?
So our DEX implementation can do about 30,000 price updates per second. And that's really like the it's not because it's saturating the network, it's because our bot traders, like the synchronization of the state, makes it very hard for you just asynchronously span the network.
That variation that were in a public setting? Or
Yeah, this was like a 5 continents deployment with 200 plus nodes. It's as close as we can make it to like something like local data. But still AWS cloud. Like I don't know what's gonna happen like with a bunch of Azure validators. What are you so yeah, that's like TBD, right? Like what we do in the cloud, we have so much control because we can ensure that it's running in like a high quality system. It's like incredibly hard to corral everybody and like get them all on board and like get all connected and do all this work.
Yeah, you can tweak the incentives, right? If they're paying fees for as a validator for being unable to cope with the demand on the network, they'll buy fiber.
Yeah.
They'll do it.
If there's that much demand, yeah, like that's our big bet is that like if there's if we like win the decentralized exchange use case, bots will eat up all the transaction space, and then validators will be like, hey, I can just make twice as much if I get 10 gigabit. Obviously, our software has to be good enough to do this, but we'll see.
I'll jump to the next one, too.
Huh?
I'll jump to the next
Yeah.
one. Yeah.
Where are you guys based in?
Next presentation, I think.
We're mostly in San Francisco.
Okay, cool.
Yeah. Cool.